Hello class, welcome to 9.3, add and subtract square roots. We are looking at two objectives, to add and subtract like square roots, to add and subtract square roots that need simplification. Okay, like square roots, like terms, like square roots means square roots that look alike. Let's write that, square roots that look alike. So to look alike, you want the square roots to have the same radicand, right? So, or identical. Let me write that out here. Identical, right? So if they match by the square root and the radicand inside it, then they are like terms. Now, if they're like terms, then we combine them just like we did with the regular numbers. Like, for example, when we did, say, 2x plus 5x, right? So for like terms, we were looking for variables that had the same, the variables must be identical, right, first. So identical variable with identical power. Let me write that here. Identical variable with identical power. They both are x's here, and they both carry the power 1. Okay. So then what we did was we simply added the 2 and the 5, the coefficients. We added the numbers, the coefficients, just kept the x with it. So 2 plus 5 is 7x, and that was how we added like terms. Right? Now with like roots, we're going to do the same thing. So let's look at the first problem. Let me illustrate it using the first problem. So here we're looking at only the radicals to identify if they're like radicals or not, like square roots or not. So I will say identical, both, okay? Radical meaning the square root. I'll just say square root with identical radicand. Right? So whatever is under the radical symbol, they must match exactly. So do we have that? Yes, we do. So just like the like terms we did, we are just going to collect these coefficients, okay, and simply put the square root of 2 next to it. So you're only dealing with the numbers, you're not really dealing with the square root itself. So 2 minus 7 is negative 5 with the square root of 2. And that is your answer. Okay. It looks a little more complex than what we're used to, but that's only because of the square root of 2 not being a perfect root. Right? We previously did approximation, right? We approximated it using the calculator. Square root of 2 gives you 1.414 when approximated. But we don't want to approximate it because that is rounding it down than its actual value. So we leave it like this in the square root symbol so that it remains in the exact form. Okay, so I'll just write it there. Leaving the answer in exact form. Okay. If we have to use the calculator on this one, then the question must have directed us to do so, and in which case it will tell us how to round it to 2 or 3 decimal places and so on. Otherwise, we just leave them in the exact form, which is not approximating it. Let's try this one. Simplify 3 root y plus 4 root y. Again, focus only on the radicands and the radical symbol. They both look alike. They are exactly the same. They're identical. So now we're free to simply collect the coefficients and attach the square root of y. That comes out as 3 plus 4 is 7 times square root of y. We just attach them. We don't put the times, but you know that they are being multiplied. They're not compatible, so you just have to shove them together, right? Just like we did it with the variables. Okay. Let's look at this one. 7 square root of p minus 6 square root of q. What do you know about these two? Well, they both have identical square root. I'll just say identical square root. but not identical radicand. One is a P, the other is a Q. If they are not identical in both respects, they are not like square roots, which means even though you could subtract 7 minus 6, meaning you're able to get a number for that, we still can't do all that here because they are not compatible to even combine. Okay? So the result is that, let's say this implies not like radical, or rather we'll say like square roots. Not like square roots. What is the answer then? Well, the answer is the same as the question. You simply cannot combine them, so your answer will simply be the question, meaning you really didn't do anything to the question. Okay, let's look at this one. 2 root 6 minus 6 root 6 plus 3 root 3. Again, observe your radicands and your radical sign. They all have a radical sign. Good. But out of these, the matching radicands only happen here between these two. So only these two are like square roots. Yeah. The square root of 3 is not compatible, which means it cannot be combined. So 2 minus 6, you only collect the coefficients and attach the common like root. So this implies the answer is a negative 4 square root of 6 plus 3 square root of 3. They're not compatible, so you can only leave them that way. You cannot go further than that. How about this one? 2 root 5n minus 6 root 5n plus 4 root 5n. Again, focus only on the square roots. They all have the same square roots. In fact, they all have the same identical radicand, 5n, 5n, and 5n under the radical. So they're all like terms, which is really nice. And so you can collect all their coefficients, 2 minus 6 plus 4, and put that common thing out here. So 2 minus 6 is negative 4. Negative 4 plus 4. Ooh. Let me write that out here. Negative 4 plus 4 is a 0. 0 times square root of 5n is 0. 0 times anything is 0, right? It was so good. I thought we were doing well. Well, we were doing well, but unfortunately, the coefficients added up to a 0. So 0 times 5n, square root of 5n, gave us a 0. What about square roots that need simplification? How do you add or subtract them? Well, let's take this problem. Square root of 20 plus 3 root 5. You look at these two, and you declare not identical. Okay. But if you look at the square root of 20, actually, it is a little premature to declare this as not identical because the 20 can be simplified. Okay. So what does that mean? So I would like you to focus on just the 20 here, and then we'll come back to the problem. So to kind of split this up to see if it can be reduced, we're splitting this number into two factors. Okay, factors are numbers that multiply to give you the 20. You want two factors, and we want one of them to be a perfect root, and the other one could be any other factor. This is the rule that we have to remember, okay, to see if there is a possibility for simplifying. Why do we need it to be a perfect root? Well, if it's a perfect root, then the radical symbol can be removed, right? That's the whole idea. So we really want the perfect root to be one of the factors. But you can find many perfect roots. So I just say, if you have many perfect roots, you want to choose the highest perfect root you can find. So let's look at 20. Well, you have many factors, right? 1 and 20, 2 and 10, 4 and 5, and so on, right? Well, this is what we have. We're not looking at negative numbers. Please understand that negative radicand will not give you positive, will not give you a real number as a solution in a square root situation. So we are not even worried about the negative side. Now, among these two, look for the pair that has a perfect root. Okay. Well, this is the pair that has a perfect root because square root of 4 is 2, right? That's a perfect root. So we're going to choose this pair. Okay. That's how we make the decision. If you had multiple options that had, with perfect roots, then you're going to choose the one with the highest, right? All right, so this would be 4, and this other factor would be 5, okay? So then I'm rewriting this 20 as 4 times 5, okay? And that can be split up as 2 separate radicals because of multiplication. You can't do that for addition. With multiplication, you can split them up like that, and square root of 4 is 2, but square root of 5 is not a perfect root, so square root of 20 will reduce as 2 root 5. Okay? So I'm bringing that down here. So square root of 20 is now reduced to 2 root 5 plus 3 root 5. Now you scan your radicals and see how it looks. Well, very clearly, this time they are, oops, I got too far there. They look identical. Now they're compatible to combine, which means 2 plus 3 can be added with the square root of 5, which is 5 root 5 as the final answer. Okay. All right, so coming back to the idea of simplification, some numbers cannot be simplified. Some numbers can be simplified. How do I know which one is which? That's where we use this particular rule, right? You see if your number can be split into 2 factors, one of them being the highest perfect root you can find. If that's the case, then there is room to simplify, and that way we won't prematurely declare the 2 radicals to be non-identical. We'd rather split them up and make them and see if they can be turned into identical factors. So let's look at this one. Square root of 48 and square root of 75, well, they both do not look identical, right? But we're going to scan and see if we can split them into 2 numbers, one of them being the highest root, okay? So for this, you really need to, excuse me, you really need to use your calculator. Okay, and here's the trick. Now, you know that some of the perfect roots are 1, 4, 9. Where am I getting this number? Well, this number comes from what we saw in 9.1, that table, right? The table which said, well, if I had, if I were to put the square roots like this, right? 1, 2, 3, 4 would be square root of 16. 5 would be square root of 25. Yeah, remember that table? So this is what you want to bear in mind. You want your factors to be either 1, 4, 9, not the 1, 2, 3, 4, 5, the one on the top. Okay, this row. 1, 4, 9, 16, 25, 36, 49, and so on, right? So that when you take their square root, it gives you a perfect root. And that is what we're trying to achieve here. So let's look at 48. 1 and 48, is 1 a perfect root? Yes, it is. But see if you can find a higher one, right? 1 is square root of 1 is 1. So use your calculator and you could do 2 and 48, right? That gives you 24. But why do you want to do the 2, right? You only want to pick the perfect roots. So let's not even look at the 2, even though it gives you a factor, to multiply and get 48. You want to see if 4 works, okay? So do 48 divided by 4 to get the other number. So 4 and 12, yes, that works. Because 1 is a perfect root, 4 is a perfect root. Go further, check for 9. Does 9 work? No, 9 doesn't work because 9 gives you 5.333 something, but that doesn't work. I'll continue with the list. Let's check 16, okay? So 48 divided by 16 gives me a 3. Okay? And you can go on like that, okay? 25 won't work. 36 is too big, right? Yeah. So 48 divided by 36 gives you 1.333, etc. 25, obviously doesn't work because you have an even number, 25. It's not going to help you with that. But if you wanted to, you could have tried the 25 and you'll know that that also doesn't work. Can we choose 49? No, we cannot because it goes beyond the 48, right? But again, over time, you'll begin to understand that you don't have to list all of them. You could just highlight the ones that will work. Well, in this case, I have 1 as a perfect root, 4 as the perfect root, 16 as the perfect root. But remember the rule said, let's scroll back a little bit. We said we want to find the perfect root, which is the highest among the perfect root pairs. So we have 3 pairs of perfect roots that work, but we're choosing the highest one, which is this. So I choose 48 to go with the factors 16 and 3. Let's scan the same way for 75. 75 is kind of easy because of the 5, right? 1 and 75 will work, but 1 is too trivial, right? So it really doesn't change anything then. We know the 25 is a likely candidate because of the ending, because it ends in a 5. The 25 and 3 are the factors here. That's come out really nicely. So we come back here and say, okay, 75 can be split up as 25 and 3. So I'll give it to you in one more step before I split it. So that's 16 times 3 minus 25 times 3. But 16 and 25 are perfect roots. Because of the multiplication, you can split. You cannot split if it had an addition or subtraction. So that's 25 times square root of 3. I'm a little crowded here. Okay, square root of 16 is 4. We expect that. Right? Square root of 25 is 5. I don't have to put the times in between them because when I shove them together, we know that they are being multiplied. Are these like terms? Yes, they are identical. Therefore, we can now do 4 minus 5 times square root of 3, which is negative 1 square root of 3, which is, I'm going to clear some space here. Now, when they want you to give simplified answers, we do not want the negative 1 there. So this actually means it's a negative square root of 3. And that's the simplified version. That's what you need to box. Okay? If you write it as negative 1 square root of 3, although it's correct, it is not fully simplified, and so you may be marked wrong. Let's look at the next one. 5 square root of 18 minus 2 square root of 8. Okay, again, on rough analysis, these two do not look identical. But then let's see if there is room to simplify. Again, test all those things. Okay, so let's take 18. So I would choose 1 and 18. That's the first one. Usually we don't. You can easily skip that because we're not going to use that anyway. Okay, next is 4. Does 18 division 4 give you a whole number? No, you get 4.5. Cannot use it. You need whole numbers. Okay, 1, 4, 9, right? I'm choosing it from this list. 1, 4, 9, 16, 25, 36, 49. I'm coming from that list. So 9, yes, 9 and 2. Okay. If you look at the next number, 16, right? 16 is too close to 18. You're not going to find another number that will multiply with it, with 16 to give you 18. 25 is beyond 18. And so you'll soon learn how to eliminate the options that don't work. Okay, what about 8? Same thing. I'm going to not even try the 1 and the 8. I'm just going to go with the 4. 4 is the highest possible square root you can find. 4 and 2. So you have 5 times 9 times 2 minus 2. The 2 and the 5, they were outside the radical, so please tag them along. All action is happening inside the radical, so keep that there. Okay. And then we're going to now simplify them by splitting them up. So that becomes 5 times, if you want, you can put it explicitly there, so that you know you're multiplying and draws your attention to that. That's the first one. I split up the radicals. Again, remember the 5 is just tagged along. All action is with the radicals. Likewise, the -2 is tagged along in the next step, but the split happens only with the radicals. Okay? So that, just for our understanding, this becomes a 3, this becomes a 2. Let me put a dot in between them just in case. So 5 times the square root of 9 is 3, times square root of 2, minus 2 times square root of 4 is 2, times square root of 2. Now, the numbers that are not radicals can be easily multiplied, right? 5 times 3 is 15, square root of 2, 2 times 2 is 4, square root of 2. Now that it's completely simplified, this is a good time to check if they are identical. And yes, they are. That allows us to simply subtract the two numbers, 15 minus 4, and put the square root next to it. This implies 15 minus 4, which is 11. Square root of 2 is our final answer. Okay. What happens if you had letters involved in your radicands? Let's take a look at that as well. So 2 square root of 50 r power 8 plus 4 square root of 54 r power 8. Now, if you look at the radicands, the r power 8 is matching, but the 50 and the 54 are mismatched. And moreover, r power 8 can be further simplified. Okay. So this is what we're going to do. We already saw that the numbers will have to be split as two factors. And if it is r, okay, you look at, okay, let me just zoom out the r power 8 alone separately. 8. So what we're trying to do is look at the power. If it is even power, life is easy, okay? If it's even power, life is easy because all you have to do is write the r power 8 as r power something, the whole squared. Because remember, the square and the square root will undo each other. So you're trying to rewrite the r as a square. So r power what will give me a square? So r power 4 times 2 will give me 8 because 4 times 2 is 8. It's again using the power rule of exponents. And with that ease, you can rewrite your any even power as something squared. Okay. Now let's consider, well, for this problem that it takes care of it. But let's say you had an odd power. Okay. Then we have extra work to do. Okay. Because r power 9 cannot be written as something squared. Okay. But the power 9 can be split up as the highest power, even power, 8, times r power 1, because this is the product rule in exponents. Product rule says if we add the powers, we should get back the power 9, right? Meaning the power 9 can be split up as a sum of two powers. But here, remember, we want the highest even power because that could be split up. It is always going to be 1 and the number before it, right? So if you're taking 9, you're splitting up as 1 and the one number before 9 is 8. If you have r power 11, then it's going to be 1 and the number before 11, which is 10, because that will be the highest even power you can find. Okay, r power 121 will be r power 120 times r power 1. So it's always going to work this way, which is really nice if you have odd powers. And we just saw that r power 8 can be written as r power something power 2, whereas this r power 1 cannot be simplified, so it has to be left that way. So this will be r power 4 the whole squared times r, which is r power 1. So if it's even power, simply write it as power 2, something power 2. But if it's odd, first split it as highest even power and 1, and then do what we did for even power. Okay. All right, coming back to our problem, we have 50. Again, this is a separate situation because you're going to split up the 50 as two separate numbers. And again, looking for the highest root, square root, 25 and 2 will work. Okay. And for r, let me use red for all of these. 25 and 2. And this comes out as r power 4, the whole squared. Okay. That's the plan for the first term. The plan for the second term, again, look at 54, okay? See if it is divisible by 2. Yes, we know it's divisible by 2. That's 27. Then look at 54, see if it's divisible by 9, okay, which is 6. Nice. I hope you're tracking with me. So what I'm trying to do is, for 54, I'm doing 2 and 27. Not 2. Yeah, 2 and 27. 54 and 4. 2 doesn't work. We don't even need the 2. Okay. 4 gives you 13.5, useless. Then go for 9. 9 gives you 6, which is good. Okay. And see if you can find something higher. So we're going to try 16. Okay. 54 divided by 16. See if that gives you a number, a whole number. 16. 3.375. Well, we're losing it right there, right? The next one after 16 is 25. That is clearly not going to work, and thereafter it's going to become bigger. So we got the two numbers as 9 and 6. And r power 8 was matching, so that's going to be r power 4. And even though they're matching, you still have to simplify, right? All right, so now let's put all of these in perspective. The 2 outside the radical is tagged along, no work there. And action inside the radical is, you have 25 times 2 times r power 4, the whole square, plus the 4 outside the radical is then brought down. And this is written as, 9 times 6 times r power 4, the whole square. Yeah? Now let's split them into separate radicals. Let's put the dot there. So 25 times square root of 2 times square root of r power 4, the whole square, plus 4, oops, we're trying to split them up, times square root of 9 times square root of 6 times square root of r power 4, the whole square. Okay. Now let's simplify this. 2 times square root of 25 is 5. Square root of 2, not a perfect root, so you're going to keep it like that. R power 4 and the power 2, remember? Again, let me put that quickly here. The 2, the square root and the power 2 will undo each other, leaving us simply with r power 4 plus 4 times square root of 9 is 3. Square root of 6, keep it as it is, square root of 6 times r, again let me put that 2 there. For the root and the power will undo each other, leaving us with r power 4. Okay, that's going to be 10. I'll bring the r power 4. Again, the norm is that we leave the square root, lingering square root right at the end. Okay, that will be the last part of your term. Okay, so that's why I brought the r power 4 in front of the radical. And here 4 times 3 is 12, and then I bring the r power 4 right there, and then write the radical 6 at the end. Now look at your radicals, are they matching? Sadly, they're not matching, but they are simplified. If you look at the 6, 6 cannot be split up further, right? Because you always want to check that. So can 6 be split up as a perfect root and another factor? No, this is not going to work because the only perfect root, the highest perfect root you can find is a 1. And the other one should be a 6. 1 times 6 is 6. So this really doesn't work for us. We know it cannot be simplified. We scanned it. It cannot be simplified. So we will have to simply leave the answer as this big expression. 10 r power 4 square root of 2 plus 12 r power 4 square root of 6. And we'll box the answer. Okay. And here's the last problem. Simplify this. So let's see. Square root of 28m squared minus 3 square root of 112m squared plus 4m square root of 63. Okay. Now let's take them step by step. Okay, let's look at the first term and see how that can be split up. 28. Remember, we want to use only the 1, 4, 9, 16, those square roots, perfect roots to split this up. And it turns out that we could use the 4 and the 7 because that's the highest you can find. Right? So 16 doesn't work, 9 doesn't work, and so on. What about m squared? Well, that's looking good because you already have m squared. The square and the square root will undo each other because it's already in its simplified form. Just to draw our attention, I'm going to put that as m squared because we didn't really change anything there. Okay, 112. Let's figure out if this will, if this is divisible by 4. Well, yes, it's divisible by 4. In fact, you get a 28. So we need to keep trying for bigger numbers, right? So see if 9 will work. 9 doesn't work. Try 16, 112 and 16. Well, 16 works. Keep trying, and we'll figure out that 16 is the highest possible we can find. So I'll just write here 16 and 7. 16 times 7 is 112. M squared remains as m squared, so that is good. And lastly, this one has only a number in the square root, in the radical. So that's 63. And let's see if that's divisible. I mean, this is a small number, so you know it's divisible by 9. So we put 9 and 7. All right, let's put them all split up under the radical. 4 times 7 times m squared minus the 3, and then 16 times 7 times m squared plus the 4m. Both are outside the radical, so 4m stays as it is, times 9 times 7. Okay, now let's split them individually. Square root of 4 times square root of 7 times square root of m squared minus 3, and then we split. Okay, times square root of 16 times square root of 7 times square root of m squared plus 4m is outside. That times square root of 9 times square root of 7. Okay, we split them all individually. So now that square root of 4 is a 2 times square root of 7 cannot be simplified further, right? 7 is a prime number, so you really can't split it any further. Square root of m squared, again, look at that idea of square root and the square undoing each other. Only with letters you see that happening, right? With numbers we have perfect roots, and so you know we can identify the numbers coming out as perfect roots. But with letters, you're trying to match the powers, okay? If powers exist. So that comes out as m minus 3 times square root of 16 is 4 times square root of 7. Once again, 2 radical and the power will undo each other, leaving us with an m, plus 4m times square root of 9 is 3 times square root of 7. Okay, now let's multiply them all, and remember to collect the radical that was not simplified, that could not be simplified, at the end of the term. Okay, 2 and m, so that's 2m square root of 7 minus 3 times 4 is 12, and then the m, so 12m, and this is the one that's outside the radical. I'm sorry, that's the unsimplified radical. 4 times 3 is 12, 12m square root of 7. Okay. Right here you can see that two terms are equal and opposite, but let's wait. Now let's only focus on the radicals. Square root of 7, square root of 7, square root of 7. Wonderful, they're all identical. They're all like radicals. Therefore, we can now simply combine their coefficients. 2m minus 12m plus 12m. And then we have the square root of 7. Now this is an interesting problem because we look for the like radical. Let me write that here. Like square root. I keep saying radical because for STEM courses we say radical instead of square root because we'll be looking at all other types of square roots, all other types of roots. But here we're only focusing on the square root, so I call it like square root. But if you come down here, 2, it's not plain numbers, right? You got the letter there. So you have to see if they are like terms as well. Like terms, if you recall, we saw it in 9.1. I gave a little mention about it. You're looking for variables that look identical with identical powers. Right? So m, they are all identical variables with identical powers. Therefore, there's one more filtering. So then you will only collect the 2 minus 12 plus 2. Remember, you can only add the numbers, right? So that m that's common stays out, and there's already the square root of 7 that stays out. So 2 minus 12. Again, you could look at the negative 12 and the 12, and they actually cancel off, right? So you could do it that way. Or you could see 2 minus 12 as negative 10. Negative 10 plus 2 is 2. So you have 2m root 7 as your final answer. And that's how you completely simplify an expression that comes with numbers and letters that can be simplified. I hope this was helpful. I will see you in the next video.